Good morning, everyone. My name is Tommaso Macri, and I'm with QueRa Computing. Welcome to this new episode of the webinar series Science with QueRa. Today, we will talk about ergodicity breaking and criticality in a gauge theory quantum simulator. I'm happy to introduce my esteemed colleagues and collaborators, Anna Hudomal from the Institute of Physics in Belgrade, Zlatko Papić from the University of Leeds, my colleague Milan Kornjaca. The results of this work were presented and were posted on the archive in this presentation in this work from December of last year, and you see here the link to the archive work. Before going into the details of this work, let me say a couple of words about QuEra. QuEra is the scientific and commercial leader in neutral atom quantum computing. We were born at Harvard and MIT, and we still collaborate together to this day. As part of our commercial strategy, we offer computers and access to quantum computing services, either through the cloud or through on-prem deployments. Our headquarters are in Boston and Massachusetts, but we recently also opened offices both in the UK, at Harwell, and in Tokyo, in Japan. We are also well-funded thanks to the support of major organizations such as Google, SoftBank, and NVIDIA. And if you're interested in learning more, of course, feel free to reach out. Today, the outline of the presentation will be essentially the one that you see here on the slide. Will be divided in 4 parts. My colleague Zlatko will first introduce some concepts about thermalization and its breakdown in gauge theories. Then Milan will talk about how to perform or to map problems in the space of quantum simulation of gauge theories with our third generation quantum computers developed at QuEra. And then Anna will present the results of the paper with the focus on the role of criticality and defects on the ergodicity breaking on the gauge theories that we were able to simulate on our systems. We will also, at the end, make some conclusions. As part of this presentation, of course, feel free to interact with us through the chat on Zoom. We will be happy to take questions either during the presentation, and we will try to respond live, or if we don't have time, we will be happy also to connect with you offline. So with this, I would like to hand over the stage, the floor to Zlatko for the presentation of the first section of the webinar. Zlatko, thank you so much for being part of this webinar, and the floor is yours.
Thank you very much, Tommaso, and of course, thanks also to all the people in the audience. I hope you can see my screen.
Yes.
Yeah.
Very well.
Good.
We are on the outline slide right now.
Yeah, very good. Okay, so I would like to spend maybe about 10 minutes to give you some general background and motivation for this work and tell you a little bit about the topic of thermalization in gauge theories. So a very broad question that motivates our work is, how do isolated quantum many-body systems reach thermal equilibrium? And this is a question where quantum simulation platforms have been very important in trying to answer this very complicated, well, it's essentially still a mystery to some extent, because these quantum many-body systems, they live in these huge many-body Hilbert spaces, and they evolve under unitary dynamics. So we've had to rethink what thermalization means in such a context. And, you know, over the past decade or two, there have been lots of works trying to reach some sort of understanding of thermalization in that context. And these are roughly some of the main things that people have found so far. So we talk about these systems being ergodic if they basically visit all these configurations, parts of this many-body Hilbert space. They develop this repulsion of energy levels and quantum chaos. Their subsystems become maximally mixed with each other, or the eigenstates are highly entangled. And because of all this, we can use the laws of statistical mechanics to describe such systems. So the big question for today is the following. Is all of this true when we talk about gauge theories, right? Do they just follow this standard paradigm of thermalization, or is there something more interesting happening there? And we are going to study a very simple example of a U1 gauge theory in one dimension, one spatial dimension, which is this quantum link model. Gauge theories usually describe, interactions between some fermionic degrees of freedom that live on a lattice, and then gauge degrees of freedom live on the links between these matter sites. And so this quantum link model basically truncates the gauge degree of freedom to some kind of quantum spin variable. And in the simplest case, which we will study, that's just a spin half quantum link model, where the gauge field is basically just represented by standard spin raising and lowering operators. So the model of this quantum link model in 1D that we are going to study is written here. And it has these three terms: the kinetic term, the mass term, and the electric field term. The kinetic is basically term is just hopping of these fermions from between different sites. And that hopping is mediated by this gauge term, which is encoded by this spin degree of freedom. The mass term is given here. So it's basically a staggered mass term because we use this staggered fermion representation of Kogut and Susskind, where we have electrons on even sides and positrons on the odd sides. And the electric field term, which normally would be present, is actually just a trivial constant in our case, so we can drop that. Now, what's special about this quantum link model or any gauge theory is that the fact that there's, as we all know, there's a Gauss law, which links the, configuration of electric fields to the matter density locally. And this also has a discretized version in our gauge theory. So there is this Gauss law generator, which is some operator defined on every site J, which is written here. And that operator commutes with this Hamiltonian on every lattice site. And the physical states are basically those that are annihilated by this operator. So that's basically what this means, is that there is a constraint due to the Gauss law, which links the configuration of matter and gauge field, just like in a continuum, let's say quantum electrodynamics, which this model is trying to basically represent in one dimension. That constraint is actually not just fundamentally important, but it's also practically important for us because it allows us to map this quantum link model onto a very simple spin model, which is called the PXP model. And so I will just briefly tell you how that mapping works. So this is the same quantum link model that we had on the previous slide, where the particle on even side is interpreted as electron, the hole on odd side is a positron, and the electric field are just these arrows pointing left or right. So because of the Gauss law, if we look at the allowed configurations in this model on every site and the surrounding links, if we look at, for instance, the odd-even bonds, there are only these three allowed configurations due to the Gauss law. And similarly, for the even-odd bonds, we have these three configurations. So basically, by stacking these patterns, consistently along the chain, you can generate many body states. And here are some three examples of those. So we can have these states with electric flux pointing left or right and no matter sites in them occupied. Or we can have this state, which is a charge proliferated state, where we have the maximum number of electron-positron pairs in this lattice. Now, because of the Gauss law, basically the configuration of these matter sites is completely fixed by the electric fields. So we can totally eliminate the matter sites altogether. And we can map all these configurations one-to-one onto states of a spin model, where the spin states are these black and white dots. So for the odd-even bonds, we use these three states that map to these ones. And similarly, the rule for the even-odd bonds is just these three states that provide the mapping to these ones. So applying this, you can simply convert all these states from the quantum link model to the spin model. So these electric flux states, they become these Z2 states where every second spin is excited. And this charge proliferated state becomes this vacuum state in the spin language. So formally, if you want to express this as a Hamiltonian, this is this PXP spin half Hamiltonian, which describes exactly the same rules that I just told you about. And so basically that's a very simple model where we have this Pauli sigma X matrix, which is converting these spins between their two basis states. And then that matrix is dressed by this projector P on one of these spin states, the white circle. And finally, that was the kinetic term of the quantum link model. And the mass term simply becomes this chemical potential term, which counts how many spins are in this excited state that we call the black circle. So the Gauss law formulation in the spin language is very simple. It just means that we don't have excitations that have neighboring, that we don't have two spins that are excited and neighbors to each other. So all of such configurations have to be removed. And so that's a very simple model that represents our quantum link model. And the question we want to know is, how does this model thermalize in the sense that I described to you already? And the short answer is it thermalizes in some sense, but not quite. So there is something called weak ergodicity breaking happening in that model. So first of all, if you just look at this level statistics that I mentioned, you find that it converges to this distribution, which is the Wigner-Dyson distribution. And that's consistent with a chaotic system. But then when we started looking at these things and many other people more carefully, we saw that there are some exceptions to that thermalization. So for instance, if you prepare this PXP model in one of these Z2 states that I mentioned, it exhibits this kind of revival dynamics, which suggests that it's able to remember that initial state after very long times. And also, if you look at the overlap of that state with the energy eigenstates, you see that there are these tower structures that run through the spectrum. And so there are these special non-thermalizing eigenstates, which are known as quantum many-body scars. So all of this constitutes basically what we call a weak breakdown of ergodicity. And the interesting thing is that this doesn't happen due to some symmetry or integrability. It's a kind of new universality class of thermalization breakdown. So as you see, people already understood some of these things about how thermalization can break down. But what really motivated us is really to ask this question, what else is left to understand about this model? And that's basically how I would like to conclude, to give you a preview of what Milan and Anna will tell you about later, which is really what are the open questions here related to thermalization in this quantum link model. So first of all, if we think about the equilibrium phase diagram of this quantum link model as a function of mass, we know that it has this phase transition between a disordered phase where we have a unique ground state, which is this charge proliferated state or this vacuum state in the spin model. And there's another ordered phase where the ground state is twofold degenerate. So there are these Z2 states or these flux states that form degenerate ground states. And so that phase transition is a second order phase transition, and it's in the Ising universality class. And in some of these theoretical works, people also determine that what value of the mass that actually happens. Now, this is important because when we do experiments, for instance, in this first experiment by Bernier and others, where they saw signatures of quantum many-body scars the first time, they actually use this diagram to prepare the Z2 state, which is over here, starting from this polarized state and ramping the mass across this critical point. So in that experiment, they just ramped the mass to infinity to prepare the Z2 state, and then they saw these nice oscillations which are related to quantum many-body scars. Now, you could easily imagine a more general protocol where you start in the ground state at some initial value of the mass, so somewhere, let's say over here, And then you evolve with the Hamiltonian with a different mass, mf, and mi and mf can be in principle different from each other, right? You can pick whatever values you like. So the question is, for what choices of this mi and mf are you going to get ergodicity breaking and these scar signatures? That's one question. The variation of that question is, what if we stop precisely at the critical point? So if I, let's say, start to ramp from here and I stop exactly the critical point, should I get these scars or not? So there is actually some previous theoretical work which suggested that the scar dynamics should disappear in that case. But, as you will see, we will have something interesting to say about that. And the final question is, what is the role of defects in this state preparation due to Kibble-Zurek mechanism? Because we know that if you ramp a system across a second order phase transition, then you should get these defects of disordered phase embedded in the background of your ordered phase. And so you might expect that this will play some important role for the subsequent dynamics when you quench the system. And so this is the one of the final questions that we will tell you about today. So I think I'm going to now pause here and maybe see if there are any questions, or otherwise I will pass it on to Milan. Do we have any questions? I don't see anything, so maybe Milan can take over then.
Sure. Thank you, Zlatko, for the fantastic introduction into the physics that we are talking about today and open questions in it. So what I'm going to touch upon is sort of how can QuEra's Rydberg platform, specifically analog quantum computer of QuEra, address some of that physics. Okay. So let me first just briefly introduce sort of the operating principles behind neutral atoms in both analog and digital modes. So at QuEra, we use atoms of rubidium 87 and trap them in optical tweezers, and then use various levels of rubidium to operate in two different modes. One is analog mode, where the atoms are loaded into traps, and after that they are static. And the other is digital mode, where we can also dynamically move the atoms during computation itself. In the analog mode, we use the fact that if you excite Rydberg atoms to a very highly excited state, their polarizability is large, and thus if two atoms are close to each other, they have are very strong interactions acting between them, or the van der Waals form. And that enables us to entangle them while we use lasers to sort of drive them between the two levels. In the digital mode, we use extra levels of Rydberg atom, in particular when we're storing the qubit in between the gates. We use hyperfine states of the rubidium, which allow us to have very long coherence time, while when we're doing entangling gates, we still excite the atoms into Rydberg states and sort of derive entanglement from there. For today, we're going to talk about analog mode, here represented by our first generation Aquila quantum computer. Although stay tuned, and as Tomaszu mentioned, our first generation digital quantum computer Gemini is being deployed in Iceland, Japan. So if we talk about Aquila, what we're really talking about is Rydberg Hamiltonian, sort of the model describing the interactions of our atoms and the laser fields we're putting into that is sort of in tuned in a few programmable and time-dependent parameters. So what do we mean by this? So first, when we put our atoms into array, we have a freedom of sort of choosing the atom positions, as long as that is within the constraints of the hardware. And that sort of allows us to tune the connectivity and sort of tune the interactions that we have here, which are this van der Waals form. The second thing when we do to atoms is drive them between the ground and highly excited Rydberg states by a coherent global drive. And for this drive, very importantly, we can tune both its amplitude in time and also its phase in time. Next, we can detune the atoms away from the Rydberg state, which sort of gives us a different cost to the excitations that we're doing to the atoms. And as we'll see, this has direct consequences for probing the lattice gauge theory, as Zlatko talked about. And lastly, not only can we sort of globally tune sort of this excitation cost, we can also add local weights and scale, which are all time dependent. And the regime of this Hamiltonian that's of particular interest to what Zlatko has talked about is the regime where we sort of put atoms close together such that the first neighbor interaction between the atoms is much stronger than other relevant energy sort of quantities in a system, such as the Rabi drive and the excitation cost. And in this case, sort of the Hamiltonian sort of becomes this PXP Hamiltonian Zlatko talked about that has a direct mapping to lattice gauge theories. In particular, what survives from a Hamiltonian is mainly sort of the excitation creation, as long as they follow the PXP constraint, and the cost of the excitations itself. And with this Hamiltonian, both the full Rydberg Hamiltonian and its sort of constrained PXP version, we saw in the past many applications and quantum simulation in optimization, in particular maximum independent set solutions, and machine learning, where we did a lot of reservoir computing. However, what we're concentrating today is quantum simulation, and there Aquila has produced sort of a cornucopia of works that touch high energy physics, quantum matter, and even chemistry. And here I just show some of them. Particularly, I would like to point out something that's quite related to what we're talking about, and that is in 2D, Aquila was able to probe confinement and string breaking. And then across the lattices in the sort of frustrated setting, we were able to see many null quantum phases, including tremor spin liquids and quantum floating phases. And not only that, we're also able to test sort of critical properties in these phases, such as shown here, for example, on the leaf lattice, where Aquila probed multi-criticality and metastability. And last but not least, sort of the native mode of Aquila is studying quantum dynamics. And there's a rich space in terms of thermalization, its breakdown, and dynamical phase transitions that Aquila has probed. And really, what we're talking today sort of brings together many of these aspects that were previously studied on Aquila. So we have ergodicity breaking, sort of probing fundamental dynamics in the system. Of course, we have lattice gauge theories showing how our Hamiltonian maps to sort of prototypical problems of interest across the field. And we also have the criticality itself playing important role in sort of bringing new physics infos. So how is it actually done experimentally? Well, I talked about the freedom of the spatial arrangement, and really what we're looking at here, we're looking at 1D chains. However, we use sort of two different configurations. One of them is this 6 parallel short chain configuration, and that has been used for a bulk of data collection, and it sort of employs the whole accessible user volume in the system in order to get as much data as possible, since the chains that are spread apart sufficiently effectively don't interact, and we can use sort of the volume of the system for parallel calculation. And then in order to probe the system size scaling of the effects observed, we also sneak through one long chain, sort of showing how you don't have to be limited by the linear dimensions of the system, but can extend further. And of course, the distance between the atoms in each chain is such that the very strong blockade constraint and the PXP Hamiltonian are observed. The next step, and that is the first step in what Zlatko has been talking about previously, is how do we get this initial state, sort of this psi of with initial mass. And this is sort of done with the bread and butter of Aquila in many experiments, and that is adiabatic state preparation, where we start from its native initial state with all zeros, and then tune these excitation cost or mass in the lattice gauge theory, and sort of smoothly connect the two in with a smooth time profile for this excitation cost, and then bring us anywhere or within the sort of phase diagram of the model, and here in particular towards the Z2 order phases or the criticalities. And lastly, the last part of the protocol corresponds to the quench, where we sort of take now this initially prepared state and rapidly change the tuning, which changes the lattice gauge theory best. And then as a function of time, after that sudden quench, we measure local observables that are accessible experimentally. And from these local observables, we can gain insight into important lattice gauge theory quantities, which Anna will talk about more. So without further ado, Anna, please, let's see what kind of physics do we observe.
Okay, so thank you very much, Tommaso, Zlatko, and Milan. So far, we have heard about the breakdown of thermalization in lattice gauge theories and how it's possible to simulate such models using QuEra's Aquila device. And now I'm going to tell you about the results of our recent work. So we are interested in the dynamical phase diagram of the PXP model with an addition of a chemical potential, or equivalently, the U1 spin 1/2 quantum link model with non-zero fermionic mass. Now, Zlatko has explained before that at a certain critical value of the mass, the system undergoes a second-order Ising-type quantum phase transition. So this means that the nature of the ground state is changing. It goes from a non-degenerate to a double-degenerate ground state. And in order to explore this phase diagram, we prepare the ground state at some initial mass and quench the system to a final mass and let it evolve. Now, a useful quantity to look at is a local observable called density of matter fields in the quantum link model. So this is experimentally measurable, and it's closely related to the number of Rydberg excitations in the actual physical setup. So because we want to identify those regimes where we have ergodicity breaking in the form of strong oscillations due to quantum antibody scarring, a useful quantity to compute is the mean squared deviation from the thermal ensemble. And this is exactly what is plotted here in this numerical phase diagram of this model. The interesting regions are in red. This is where we have ergodicity breaking. So region 1 is actually the conventional scarring related to the null state in the PXP model, or in the quantum link model language, this is the vacuum state with zero particles. And this was actually the first state, the first quantum antibody scarred states to be experimentally studied using Rydberg atoms. Region 3 is what we call unconventional scarring. So this is related to the polar state in the PXP model, or equivalently the charge proliferated state in the quantum link model. So this is the state with the maximum number of particles. And this state only becomes scarred if you tune the fermionic mass to a certain non-zero value. So this was also studied experimentally on a tilted Bose-Hubbard quantum simulator. But probably the most interesting region here is this region 2. So this was numerically discovered. And so it's a continuous family of quantum antibody scarred states. And it stretches all the way across the quantum phase transition to the nil state. So previous works have expected that scarring should disappear at the critical line because the Z2 symmetry of the ground state is disappearing, but it was numerically shown that this is not happening. So we wanted to test this experimentally, and in order to do this, we chose 3 cuts through the phase diagram. So cut C1 goes through this partly to this continuous family of quantum antibody scarred state. The cut C2 is exactly at the critical line in the thermodynamic limit, and C3 is close to the nil state regime. Now we can measure the dynamics of the matter density. So these are the actual experimental results for 2 points along the critical line, for example, and we can clearly see a difference between non-scarred and scarred regimes. So here, when we have scarring, we see persistent oscillations, and we can use these results to compute the deviation from the thermal ensemble. So these are the results along the 3 cuts. The blue and red points are the actual experimental results, and the dashed black line is the raw numerical result. But the numerics is the ideal case. In the experiment, we always have some decoherence from environmental effects, and we model this decoherence by simply adding some exponential damping. So this alpha exponential decay coefficient was determined empirically, so it's the same for all the points along all 3 cuts, and it's represented by the dot dashed line here. So this gives us excellent agreement between the experimental results and numerics. So the blue points are for shorter chains of 21 atoms, and so this can be directly compared to the numerical simulations based on exact diagonalization. But we also wanted to test this in larger systems, so we chose a few representative points along each of the 3 cuts. So these are the red points, and this corresponds to a much longer chain of 61 atoms. So this is far beyond what can be done using numerical simulations based on exact diagonalization. So we can see that the phase diagram is not significantly changing with the system size. So this was the first experimental realization of this continuous family of quantum many-body scarred states, and we have showed the scarring indeed persists at the critical line. But what was particularly interesting is that this critical ground state, the phase transition, not only that it is scarred, it's one of the best reviving points in the whole phase diagram. So we focus here on this particular point. So it's along the critical line and for some value of the fermionic mass. So unlike the null state and the polarized state, which are product states and therefore have zero entanglement entropy, this state is very much entangled. Actually, the entanglement entropy is diverging with system size, but we still find robust oscillations, so both in the numerics and the experiment. So why is this happening? So usually when we study quantum many-body scarring, we look at the overlap of the initial state, in this case the critical ground state, with all the eigenstates of the Hamiltonian which governs the evolution. And now we find towers of scarred states as expected. And the highest overlap states are in the low energy part of the spectrum. And it turns out that a good approximation for these eigenstates are pairs of Magnon excitations. So this is shown here by the red line. And for this special value of the fermionic mass, these Magnons are particularly weakly interacting. So as you add more and more Magnons, the energy of the total state is going to be approximately a multiple of a single Magnon pair energy. So because of this, the towers are equidistant. And we can also look at the energy dispersion of a single Magnon state. And for this special value of the mass, this dispersion is approximately flat. So because of this, eigenstates which are close to the highest overlap scarred states have approximately the same energy. And this is making the towers very sharp. Now, if we have sharp and equidistant towers, our initial state is approximately a superposition of equally spaced scarred states. And this makes the oscillations very strong and robust. But the mechanism behind this is yet to be completely understood. So another thing that we're interested in are the effects of defects which appear during the state preparation protocol due to the well-known Kibble-Zurek mechanism. So if we prepare the system in the ground state and slowly change some control parameter, after a certain relaxation time, the system will move into the new ground state. But the thing is that this relaxation time is starting to diverge as you approach the critical point. So it doesn't matter how slow your ramp is, you will always come to a point where it takes you less time to reach the quantum phase transition than it takes the whole system to relax into the new ground state in the other phase. So what's going to happen then is that separate parts of the system are going to separately cross into the new phase. So separate domains are going to form. And in between those domains, topological defects in the form of domain walls will appear. And the number of these domains depends on the speed of the ramp in the vicinity of the phase transition. So if your ramp is slow, you will get longer domains and less defects. If your ramp is fast, you will get shorter domains and more defects. But this is only telling you about the properties of the state which is prepared after the ramp. We wanted to go one step further and to test what is the effect of these defects on the dynamics after the quench. So in order to study this, we choose a regime with strong oscillations. So this is cut 3, close to the nil state. And the state that is prepared in this case is approximately the nil state with some defects on top. So these defects are typically in the form of neighboring ground state atoms, as shown here in red. Or if we translate this into the quantum link model language, this is just a vacuum state with a few particles on top. So because in the experiment, the time that we have for the state preparation and measurement is limited, we cannot simply change the slope of a linear ramp. So instead of this, we chose this sigma type ramp, which is based on this function here. And the important parameter is this curvature parameter k. So if k is close to 0, the ramp is approximately linear. And if as k approaches 1, the ramp becomes more and more flat in the vicinity of the critical line. So these are the actual experimental results that we get for two different values of k. This is the matter density at different sites. So if the ramp is slow, we see some very nice and persistent oscillations. But if the ramp is faster, we get more defects and the oscillations are decaying quickly. So there's a visible effect. And we can also look at the dynamics of the domain wall density. So the neighboring ground state atoms are not the only type of defect, so they're related to the matter density. We also have another type of domain walls, which are neighboring Rydberg excitations. And in the quantum link model language, they represent gauge violations, so violations of the Gauss law. But the good thing is that such domain walls are strongly suppressed by the Rydberg blockade. And we can look at the actual numbers, both in the numerics and the experiment. The number of such defects is very low, which is great because it means that this Rydberg atom platform is a great approximation for the quantum link model that we want to study. Now we can plot the dynamics of the domain wall density for two different values of k. So there is a small but noticeable effect. So the decay rate is different. And now we can extract the domain wall density in the initial state in both the numerics and the experiment. And we can look at the dynamics after the quench, perform a Fourier transform, and extract the height of the highest Fourier peak. And these two quantities are plotted here and compared. And we can see that in the numerical result, we have excellent agreement up to k 0.5. So as you improve the ramp, as it becomes slower in the vicinity of the critical line, you get less and less defects in the initial state, but also you get stronger oscillations after the quench. And if k is too large, as it approaches 1, this is again not great because here we have a finite size system. So it's not exactly a critical line, but the critical region, the whole region where the gap is small. So it's not great if your ramp is too steep, then too flat, then too steep again. So the optimal value of k would be somewhere around 0.8. And we also see the same trend in the experiment, the decreasing number of defects and stronger oscillations. But in both cases, we are seeing some deviations for k larger than 0.5. So we were wondering, is the density of defects the only thing that is important, or also the type of defects? And this is what we investigate here. So we divide the defects into two different classes. So if we have even numbers of ground state atoms neighboring each other, in the quantum link model language, this corresponds to unpaired particles. So 1 or 3 or less likely 5. And such unpaired particles are domain walls between the domains of electric field in the opposite directions. And another class of defects are odd numbers of ground state atoms, and they correspond to paired particles and antiparticles in the quantum link model. And they separate domains where the electric field is in the same direction. And it turns out that this has a strong effect on the dynamics. So these are numerical results for the electric field on each site. So if you have paired the defects, all the domains of the electric field are in the same direction, and we see some persistent oscillations. So this is because it's very easy to remove such defects. You simply excite this one atom in the middle, and you recover the full nil state. But if we have unpaired defects, the direction of the electric field will be alternating between the domains, and the oscillations are decaying much faster. So if you wanted to restore the full nil state, you would have to flip every other domain. So that is not so easy to do. But what was particularly interesting is that the proportion of these two types of defects is changing with k. So as you improve the ramp, the number of detrimental defects is decreasing in both the experimental results and the numerics. And the question is, why is this happening? So this is not explained by the conventional Kibble-Zurek theory, because Kibble-Zurek says that separate domains are not supposed to communicate with each other. And here we are seeing that the domains are becoming more and more aligned. So this is still an open question. Why is this happening? So to conclude, we have shown that Rydberg atoms provide a very versatile platform for studying ergodicity breaking in lattice gauge theories. We have for the first time realized this continuous family of quantum antibodies scarred state in an experiment. And we have shown that scarring not only survives at the critical point, but it turns out the scarring is very strong for this critical ground state, which has very large entanglement. But the mechanism behind this is yet to be completely understood. We have also studied the effects of defects on the dynamics, and potentially a refined Kibble-Zurek theory will be needed to completely explain the observations, why the domains are becoming aligned. And this is not the end. There are many other things that can be done with this platform. For example, a natural extension would be to study two-dimensional Rydberg atom arrays, because in 2D we can play with the lattice geometry and see what are the possible, if this has some effects on the phase diagram. Or we could also try to engineer other types of gauge theory. For example, in 2D we could try to do non-abelian gauge theories. Or another research direction would be to add some other ingredients to the model, for example, to add periodic driving, which was shown to stabilize and enhance the effects of scarring if the driving parameters are appropriately chosen. And we also know that the driving can be used to erase certain types of defects. So, but these are all topics for future work. So thank you very much for attention, and let me see if there are any questions.
Thank you so much, Anna, Zlatko, and Milan for the great presentation. I just as part of the conclusion, I added my email. If any of you has any questions, feel free to reach out. We would be happy to continue the conversation offline. Thank you so much, and looking forward to seeing all of you at the next episode of the webinar series Science with QuEra. Thank you so much. Thank you, Zlatko, Anna, and Milan again.
Thank you.